Imagine a planet not circling a warm, steady star like Earth does, but instead moving through space under the gravitational command of a black hole. At first, the idea sounds like pure science fiction, a place of instant destruction where nothing living could survive. Black holes have a reputation for swallowing everything, crushing matter, stretching space and time, and erasing all familiar rules. Yet the universe is rarely as simple as our fears suggest. When examined carefully, the idea of life on a planet orbiting a black hole becomes not a fantasy, but a complex scientific question filled with surprising possibilities, strict conditions, and extraordinary consequences. To understand whether life could exist in such an environment, it is necessary to let go of the image of black holes as cosmic vacuum cleaners. A black hole does not roam the universe hunting planets. It behaves gravitationally like any other object of the same mass. If the Sun were suddenly replaced by a black hole with the same mass, Earth would continue orbiting in almost exactly the same way, at least initially. The catastrophe would come not from gravity tearing Earth apart, but from the loss of sunlight. This simple fact reshapes the entire discussion. The danger of a black hole is not universal at all distances. It becomes extreme only when you get very close. A planet could orbit a black hole safely if it remained far enough away to avoid destructive tidal forces. These tidal forces arise because gravity grows stronger with proximity, stretching objects along one direction while compressing them along another. Near a small black hole, tidal forces are violent and lethal. Near a supermassive black hole, however, the gradient of gravity at a given distance can be surprisingly gentle. This is one of the universe's strangest ironies. The biggest black holes can be the safest to approach, at least when it comes to spaghettification. In the centers of most galaxies, including our own Milky Way, sit supermassive black holes containing millions or billions of times the mass of the Sun. These giants influence stars and gas clouds over vast distances. Some stars orbit incredibly close to them and yet remain intact, following predictable paths year after year. If stars can survive in orbit, the idea that planets might also exist in these regions becomes plausible. In fact, planets could form around stars that themselves orbit a black hole, or in rare cases, possibly orbit the black hole directly if conditions allow. The first major challenge for life is energy. Life, at least as we understand it, requires a stable energy source to drive chemistry, maintain order, and power metabolism. On Earth, that energy comes primarily from the Sun. A planet orbiting a black hole would not receive light from the black hole itself, since black holes emit no light from within the event horizon. However, black holes can be surrounded by glowing accretion disks. As matter spirals inward, it heats up to millions of degrees and emits intense radiation, including visible light, ultraviolet rays, and X-rays. An accretion disk can outshine entire galaxies. From a distance, it could act like a star, bathing nearby space in energy. If a planet orbited at a safe distance from such a disk, it could receive a steady supply of energy. This energy would not be identical to sunlight. It would be harsher, richer in high-energy radiation, and potentially dangerous to unprotected life. But life is remarkably adaptable. On Earth, organisms thrive around deep-sea hydrothermal vents using chemical energy rather than sunlight. It is not unreasonable to imagine life evolving mechanisms to shield itself from radiation or to exploit different energy spectra. Another possibility is that the planet does not rely on the black hole for energy at all. Instead, it could orbit a normal star that itself orbits the black hole. In this scenario, life would experience days and nights, seasons, and a familiar stellar rhythm, while the black hole looms in the sky as a massive, dark presence. From the planet's surface, the black hole might appear as a void surrounded by a bright halo of distorted starlight, a constant reminder of the deeper structure of the universe. In such a system, gravity plays a subtle but profound role. The black hole's immense mass would influence the star's orbit, which in turn would affect the planet's climate. Orbits might be elongated, leading to long periods of warmth followed by deep cold. Time itself would behave differently. According to Einstein's theory of general relativity, gravity affects the flow of time. The stronger the gravitational field, the slower time passes relative to distant observers. On a planet deep within a black hole's gravitational well, time would pass more slowly than it does far away. This time dilation could have extraordinary consequences. A civilization living on such a planet might experience years or centuries while millions of years pass elsewhere in the universe. From their perspective, the cosmos would seem to age at an accelerated rate. Stars would evolve rapidly in the distant sky. Galaxies might subtly change over what feels like a single lifetime. This would not necessarily prevent life, but it would profoundly shape culture, philosophy, and the perception of existence. The sky itself would look unlike anything known on Earth. Gravitational lensing would bend light around the black hole, warping the appearance of stars. Some stars might appear in multiple places at once, their light taking different paths through curved spacetime. The black hole's shadow would be visible, a dark circle surrounded by a glowing ring of light. Not because the hole is visible, but because spacetime itself reveals its presence. This constant visual distortion could influence how intelligent beings understand reality, perhaps leading them to discover relativity intuitively through observation. Stability is another crucial requirement for life. Life needs long periods of relative calm to evolve complexity. Violent environments reset progress. The region around a feeding black hole can be extremely chaotic, filled with radiation bursts, jets of particles moving at near light speed, and fluctuating gravitational forces. However, not all black holes are actively feeding. Many are quiet, consuming little or nothing. A dormant supermassive black hole could provide a relatively stable gravitational anchor without constant energetic outbursts. If a planet orbited such a quiet black hole at a sufficient distance, the environment could be surprisingly peaceful. The black hole would be dark and silent, exerting gravity but little else. The primary risks would come from passing stars, gas clouds, or the long-term evolution of the system. Over billions of years, gravitational interactions could destabilize orbits. But this is also true in ordinary star systems. Stability is a matter of probability, not certainty. Chemistry would function normally on such a planet. Atoms do not care whether gravity comes from a star or a black hole. Molecular bonds form according to electromagnetic forces, which remain unchanged. Water would behave as water. Carbon chemistry would proceed as usual. The fundamental processes that enable life are local. They do not depend directly on the cosmic scale structure of space-time, as long as conditions remain within tolerable ranges. One of the more subtle challenges would be radiation. Accretion disks and relativistic jets emit intense radiation that could sterilize a planet if it were too close or poorly shielded. But planets can have thick atmospheres, magnetic fields, or underground habitats. Earth itself is constantly bombarded by cosmic radiation, yet life persists thanks to protective layers. A planet in a black hole system might evolve even more robust defenses, perhaps with life primarily underground or underwater. From the perspective of evolution, such an environment would apply strong selective pressure. Organisms that can repair radiation damage efficiently, tolerate extreme energy fluctuations, or exploit unusual energy sources would thrive. Over time, life could become radically different from Earth's, not just in appearance, but in fundamental biochemistry. Silicon-based life, exotic solvents, or entirely unfamiliar metabolic pathways might emerge, driven by conditions we rarely encounter. If intelligent life arose on such a planet, their science would develop under strange constraints. Space travel would be far more challenging. Escaping the deep gravitational well of a supermassive black hole requires enormous energy. Reaching other stars might be prohibitively difficult, effectively isolating the civilization. At the same time, their observations of relativistic effects could give them insights into physics far beyond what early human astronomers had. They might understand gravity and space-time long before discovering electricity. Communication with the outside universe would also be affected by time dilation. Messages sent outward would arrive in the future far beyond the sender's lifetimes. Messages received would come from civilizations long dead or evolved beyond recognition. This temporal isolation could shape a unique sense of loneliness or cosmic detachment, even if the planet itself teems with life. The question of whether such a planet could form naturally remains open. Planet formation usually occurs in disks of gas and dust around young stars. Near a black hole, tidal forces and radiation can disrupt these disks. However, star formation has been observed surprisingly close to the Milky Way's central black hole. Where stars can form, planets may follow. Alternatively, planets could form far away and later migrate inward, captured into stable orbits over cosmic time. Even if rare, rarity does not mean impossibility. The universe contains hundreds of billions of galaxies, each with billions of stars. Even highly improbable configurations may occur countless times. Life on a planet orbiting a black hole may be vanishingly rare in any given galaxy, yet common on a cosmic scale. The universe has a way of realizing almost every allowed possibility, given enough time and space. Perhaps the most profound implication of such life is philosophical. It reminds us that life is not tied to familiar settings. It does not require blue skies and yellow suns. It requires gradients, energy flows, stability, and time. Where those conditions exist, life may find a way, even in the shadow of one of the universe's most extreme objects. A planet orbiting a black hole would not be a place of immediate doom, but a world of deep gravity, warped light, altered time, and extraordinary adaptation. In the end, the question is not whether life near a black hole is comfortable or familiar, but whether it is possible. Physics does not forbid it. Chemistry does not forbid it. Evolution, given patience, may even favor it under the right circumstances. The universe is under no obligation to resemble our expectations. In its vastness, a living world could quietly circle a black hole, thriving in darkness, rewriting our understanding of what it means for a place to be habitable. As the planet continues its silent journey around the black hole, the deeper implications of such an orbit begin to unfold over geological time. Gravity, though steady on short timescales, slowly sculpts everything. Mountains rise and fall, tectonic plates drift, and oceans circulate under forces that feel familiar yet subtly altered. The black hole's mass influences not only the planet's orbit, but the architecture of the entire system. Neighboring stars move differently, comet paths curve unexpectedly, and the night sky becomes a dynamic, evolving map of distorted light and shifting patterns. One of the most significant long-term effects comes from orbital precession. Unlike simple elliptical orbits around ordinary stars, orbits near a massive object like a black hole precess, noticeably due to relativistic effects. The planet's path slowly rotates over time, changing the timing and intensity of seasons. These cycles could span tens of thousands or even millions of years, far longer than human seasons, but well within the evolutionary memory of life. Entire species might evolve to synchronize with these deep cycles, emerging, migrating, or reproducing according to gravitational rhythms written into spacetime itself. Climate on such a planet would be shaped by both familiar and exotic factors. If the planet receives energy primarily from a star, its climate would resemble that of ordinary worlds, but with additional perturbations. The star's orbit around the black hole might vary slightly, causing subtle changes in stellar output or distance. If the planet relies partly on radiation from an accretion disk, the climate could respond to fluctuations in the black hole's feeding rate. Periods of increased accretion might warm the planet, while quieter eras could trigger global cooling. Atmospheric dynamics would also be influenced by radiation composition. High-energy photons can alter atmospheric chemistry, breaking molecules apart and creating reactive species. Over time, this could lead to atmospheres rich in unusual compounds. Ozone layers might be thicker or thinner than Earth's, depending on conditions. Exotic aerosols could tint the sky strange colors, perhaps deep violet or copper red, as light scatters through unfamiliar chemical mixtures. Despite these challenges, life's capacity for adaptation should not be underestimated. On Earth, life has survived asteroid impacts, global glaciations, massive volcanic eruptions, and dramatic shifts in atmospheric composition. A planet near a black hole would present a demanding but not insurmountable environment. Life would evolve not to resist change entirely, but to ride its waves. Resilience would be more valuable than specialization. Flexibility would become the dominant evolutionary strategy. In such an environment, early life might emerge in protected niches. Subsurface oceans, shielded by kilometers of rock or ice, could provide stable conditions. Hydrothermal systems driven by tidal heating or radioactive decay could offer chemical energy independent of surface radiation. These environments mirror some of the most promising habitats for life elsewhere in our own solar system, such as Europa or Enceladus. From these hidden cradles, life could slowly expand outward as adaptations accumulate. As ecosystems grow more complex, entirely new forms of symbiosis might appear. Organisms could develop cooperative strategies to manage radiation exposure, with some species absorbing or deflecting harmful energy while others exploit the byproducts. Photosynthesis itself might take unfamiliar forms, using different pigments tuned to the dominant wavelengths of available light. Instead of green plants, landscapes might be covered in dark blues, purples, or even metallic sheens, optimized for strange skies. If intelligence eventually arises, its development would be shaped by constant awareness of gravity and time. Civilizations would grow up under a sky where relativity is not an abstract concept, but an observable fact. Clocks would disagree depending on altitude or orbital position. Navigation would require accounting for spacetime curvature. Even simple engineering would demand a sophisticated understanding of gravity. In such a world, physics would not be an academic discipline separated from daily life, but a practical necessity woven into culture from the beginning. Mythology and philosophy would likely reflect the presence of the black hole. It might be seen as a god, a gate, a wound in the universe, or a cosmic heart around which everything turns. Stories might speak of time flowing differently near its depths, of ancestors who ventured closer and returned changed or not at all. Even as science advances, the emotional weight of living near such an object would never fully disappear. Awe and fear would coexist with familiarity. Technological development could follow unusual paths. Energy production might exploit gravitational gradients, tapping into tidal forces or relativistic effects. Structures could be built to withstand extreme stresses, leading to materials science far beyond early human technology. However, the difficulty of space travel might limit expansion. Escaping the gravitational well would require massive investment, perhaps making off-world colonization a rare and symbolic act rather than a practical necessity. Communication with distant civilizations, if any exist, would be haunted by time distortion. Messages sent out would drift into a future the senders will never see. Incoming signals would be ancient echoes. This temporal separation could foster a sense of cosmic isolation, encouraging civilizations to turn inward, focusing on longevity, sustainability, and deep time rather than rapid expansion. Art, history, and memory might be valued more highly than novelty. From an external observer's perspective, such a planet would appear frozen in time. Watching from far away, one might see its civilization evolve at a glacial pace, while from the planet's own viewpoint, history unfolds normally. This asymmetry challenges intuitive ideas about simultaneity and progress. It reminds us that time is not universal, and that civilizations may be separated not only by distance, but by rate of existence itself. The presence of the black hole could also serve as a natural laboratory. Advanced civilizations might study it directly, sending probes closer and closer to the event horizon. They could test theories of gravity, quantum mechanics, and information in ways impossible elsewhere. For them, the black hole would not just be a threat or a backdrop, but a source of knowledge, perhaps even a partner in understanding the deepest laws of reality. Speculation often turns darker when black holes are involved, imagining eventual doom as orbits decay and matter spirals inward. But this fate is not inevitable. Stable orbits can persist for billions of years. Even when change comes, it often comes slowly. Life would have time to adapt, migrate, or transform. Extinction, when it occurs, would be part of the same natural cycle seen throughout the universe, not a unique consequence of living near a black hole. Ultimately, a planet orbiting a black hole forces us to confront the limits of our imagination. We are accustomed to defining habitability narrowly, based on Earth's example. Yet the universe operates on broader terms. It allows for worlds where time bends, light curves, and gravity dominates the sky, and still leaves room for life to arise, persist, and reflect on its own existence. This possibility does not trivialize the dangers of black holes. It does not deny their destructive power. Instead, it places them within a larger context, where destruction and creation coexist. The same gravity that tears stars apart can also hold systems together. The same spacetime curvature that threatens can also protect. In the universe, extremes are not automatically hostile to life. They are simply different. Over even longer stretches of time, the relationship between the planet and the black hole becomes part of a grand cosmic dance that spans billions of years. The black hole itself is not static. It grows slowly by consuming gas, dust, and occasionally stars. Each such event slightly alters its mass, subtly reshaping the gravitational landscape. These changes ripple outward, adjusting orbital parameters and introducing gentle but persistent shifts in the planet's motion. To life on the planet, these changes would be imperceptible within a single lifetime, yet over epochs they would become written into the geological and biological record. Continents might drift in patterns influenced indirectly by these gravitational adjustments. Ocean currents could evolve differently as rotation rates and axial tilt vary over immense timescales. Ice ages might arrive, not only due to stellar cycles, but also due to the planet's changing relationship with the black hole. Climate history would be complex, layered, and deeply tied to cosmic events far beyond the planet's surface. Future scientists of that world might read their planet's rocks the way astronomers read the stars, uncovering a narrative that links local life to galactic evolution. As the black hole grows, relativistic effects could become slightly stronger. Time dilation would increase marginally, deepening the temporal divide between the planet and the wider universe. This would not feel dramatic to inhabitants, but it would compound the already profound isolation imposed by physics. Their civilization would exist in a kind of temporal eddy, a region of space-time where history flows at a different rate. This could influence how they plan for the future, placing greater emphasis on continuity and long-term stewardship than on rapid expansion or short-lived achievements. Biology itself might begin to reflect this relationship with time. Lifespans could evolve to be longer relative to external cosmic time, though subjectively normal to the organisms themselves. Evolutionary processes might favor slower reproduction and greater stability, as environmental changes are gradual but relentless. Species could develop deep genetic memory, with adaptations unfolding over immense spans rather than rapid bursts. Extinction events would be rarer, but more transformative when they occur. If intelligent beings arise and persist long enough, they may eventually face a profound choice. They might attempt to leave the gravitational influence of the black hole, seeking regions of space-time where time flows more rapidly and connection with the broader universe is easier. Such an endeavor would be monumental. The energy required would be vast and the risks extreme. Yet for a civilization that understands gravity and space-time as intimately as their own biology, Such a challenge might be seen not as impossible, but as a defining test of purpose. Alternatively, they might choose to remain, embracing their unique position in the cosmos. From their perspective, the black hole system could be the safest place imaginable. Far from supernovae, gamma-ray bursts, and chaotic star-forming regions, their world could enjoy long-term stability. While the wider universe ages and transforms rapidly beyond their temporal horizon, they would persist, maintaining knowledge and culture across spans of external time that dwarf most civilizations. Their records of the cosmos would be extraordinary. Observations of distant galaxies would reveal accelerated evolution. Stars would be seen forming, aging, and dying in what feels like compressed time. This would grant them a kind of cosmic foresight. They could witness trends in galactic evolution, dark matter behavior, and large-scale structure formation with clarity unmatched elsewhere. In a sense, they would live near the universe's slow-motion center while watching everything else fast forward. This vantage point could lead to a unique form of cosmology. Their understanding of the universe would be deeply time-relative. Concepts like past, present, and future would be treated as local phenomena rather than universal truths. Philosophy might abandon linear narratives in favor of layered temporal models, where events are understood differently depending on one's position in space-time. Identity itself might be viewed as something that exists across time gradients, not fixed moments. Art and expression would likely reflect this worldview. Stories might span epochs in a single narrative. Music could be composed around rhythms inspired by orbital periods and relativistic cycles. Architecture might align with gravitational vectors, designed not just for aesthetics or function, but to harmonize with space-time curvature. Even language could evolve to encode temporal nuance more richly than human languages do. Despite all this strangeness, daily life on the planet might feel surprisingly ordinary to its inhabitants. They would wake, work, form relationships, raise offspring, and contemplate their place in existence much as humans do. The extraordinary becomes mundane when it is all you have ever known. The black hole would be a constant presence, but not a constant terror. It would be part of the background of reality like gravity and sky are to us. From the outside, such a world challenges our deepest assumptions about habitability. It forces us to confront the idea that life does not need comfort, only possibility. It does not need familiarity, only consistency. A black hole does not automatically negate these conditions. Under the right circumstances, it reshapes them. The possibility of life orbiting a black hole also reframes our search for life in the universe. It suggests that we should not limit ourselves to looking only at Earth-like stars in calm regions of galaxies. Life may exist in places we once dismissed as too extreme, too dark, or too dangerous. The universe may be far more inventive than our caution allows. In contemplating such worlds, we are reminded that black holes are not merely cosmic destroyers. They are sculptors of galaxies, anchors of structure, and laboratories of extreme physics. They influence where stars form, how galaxies evolve, and possibly where life can arise. Their role in the cosmic story is not solely negative. It is complex, subtle, and deeply intertwined with creation itself. As the ages unfold, the planet's relationship with the black hole becomes less a matter of survival and more a matter of identity. The black hole is no longer simply an object in the sky or a source of gravity. It is the central fact around which history, science, and self-understanding are built. Every calendar, every long-term prediction, every model of the future is calibrated against its mass, its spin, and its slow, patient influence on space-time. To live on such a world is to grow up knowing, at a fundamental level, that reality itself is curved. The spin of the black hole introduces another layer of complexity. Many black holes rotate, dragging space-time around with them in a phenomenon known as frame dragging. This effect subtly twists orbits and alters the paths of particles and light. For the planet, this could mean that space itself is never entirely still. Directions have a preferred twist. Motion carries a faint asymmetry. Over evolutionary timescales, even biology might internalize this bias. Organisms could develop asymmetrical structures or behaviors aligned with the underlying rotation of spacetime, much as life on Earth is shaped by planetary rotation and magnetic fields. If the black hole's spin is high, it could power relativistic jets that extend far into space. These jets would not necessarily threaten the planet if it lies outside their path, but their presence would be unmistakable. From the surface, they might appear as immense columns of light stretching across the sky, steady for millions of years. Such features would dominate mythology and symbolism. They could be interpreted as cosmic rivers, axes of creation, or conduits to other realms. Even a scientifically advanced civilization might preserve ritual or artistic traditions inspired by their awe-inspiring permanence. The planet's magnetic field would play a crucial role in maintaining habitability. Charged particles from the accretion disk or jets could otherwise strip away the atmosphere. A strong magnetosphere could deflect much of this radiation, creating luminous auroras that dance across the skies. These auroras might be far more intense than Earth's, illuminating entire nights with shifting curtains of color. Over time, they could become integrated into cultural practices, marking seasons, celebrations, or warnings of increased activity near the black hole. Life, always opportunistic, could even learn to exploit these phenomena. Certain organisms might harvest energy from charged particles or radiation directly, converting what would otherwise be harmful into sustenance. This would represent a radical departure from Earth-based life, but not a violation of physical law. Nature repeatedly demonstrates that when energy flows exist, life finds ways to tap into them. As ecosystems diversify, the biosphere might become stratified not just by altitude or depth, but by radiation tolerance. Surface life could be transient and hardy, while more delicate organisms thrive underground or underwater. Entire evolutionary lineages might never experience open sky, evolving senses tuned not to light, but to vibrations, magnetic fields, or chemical gradients. Intelligence, if it arises among such beings, could be deeply alien in its perception of reality, grounded in phenomena humans barely notice. Yet intelligence might also arise among surface dwellers, shaped by constant exposure to the warped heavens. Their sciences would naturally incorporate relativistic corrections from the start. Children might learn that clocks disagree before they learn arithmetic. Education would emphasize uncertainty, relativity, and context as fundamental principles rather than advanced concepts. This could produce a culture unusually comfortable with ambiguity and complexity. Ethics, too, might be influenced by their cosmic circumstances. Living in a place where time itself is variable could weaken the idea of absolute simultaneity and shared experience. Moral systems might focus more on local consequences and long-term continuity than on universal rules. Responsibility could be defined in terms of preserving stability across time gradients, ensuring that actions taken now do not produce disproportionate effects far in the future. The planet's future would not be free from existential threats. Passing stars could perturb orbits. A sudden increase in accretion could flood the system with radiation. Over trillions of years, even supermassive black holes slowly evaporate via Hawking radiation, though this process is unimaginably slow. These are not immediate dangers, but they remind us that no environment is eternal. Survival would depend on foresight, adaptability, and perhaps eventually migration. If a civilization reaches a level where it can manipulate gravity or space-time itself, the black hole might become more than an object of study. It could become a tool. Theoretical physics suggests that rotating black holes contain enormous amounts of extractable energy. A sufficiently advanced society might tap into this energy to power its world indefinitely, achieving a level of sustainability far beyond anything possible around ordinary stars. In this sense, the black hole could be not a liability, but the ultimate renewable resource. There is also the haunting question of the event horizon itself. From afar, it is simply a boundary. From nearby, it is a place where the known laws of physics strain and perhaps break. A civilization living so close might feel an irresistible pull to understand what lies beyond. Probes could be sent, gathering data until signals stretch and fade. The loss of these probes would not be sudden, but gradual, their transmissions slowing, reddening, and finally freezing at the edge of perception. This slow disappearance could become one of the most profound experiences in their scientific history. Such experiments would blur the line between observation and philosophy. What does it mean to know something that can never be reported back in full? What does it mean for information to cross a boundary that time itself cannot escape? These questions, debated abstractly on Earth, would be immediate and visceral realities for such a civilization. Through all of this, the simple fact remains that life endures. It grows, adapts, thinks, and wonders, even in the shadow of a black hole. The presence of extreme gravity does not erase the basic drives of living systems. To persist, to understand, to find meaning in existence. In that sense, a planet orbiting a black hole is not an exception to life's story, but an extension of it. As centuries turn into millennia and millennia into deep epochs, the slow constancy of the black hole begins to feel almost comforting to the life that has grown beneath its influence. While stars elsewhere flicker and die, while galaxies collide and reshape themselves, the gravitational presence at the center of this system remains steady, predictable, patient. For civilizations that value permanence, the black hole becomes a symbol of endurance. It does not rush. It does not age in any way that matters on biological timescales. It simply exists, anchoring everything around it. This permanence could profoundly influence how life on the planet understands death and continuity. Individual lives would still be fragile, but the cosmic backdrop would feel eternal. Cultural traditions might emphasize legacy over immediacy, long memory over instant gratification. Knowledge could be preserved with extraordinary care, not just for future generations, but for futures so distant that external civilizations might rise and fall unnoticed. History would not be measured in centuries, but in orbital cycles and relativistic epochs. The sciences would naturally converge toward unification. On a world where gravity visibly bends light and alters time, it would be impossible to treat physics as fragmented disciplines. Astronomy, geology, biology, and cosmology would be deeply interwoven. Life itself would be understood as a space-time phenomenon, something that arises not merely from chemistry, but from the structure of the universe at every scale. This perspective could lead to insights that are difficult to achieve in more ordinary environments. One particularly intriguing consequence would be the study of causality. Near a black hole, the distinction between cause and effect can become blurred when viewed from different reference frames. Events that appear simultaneous to one observer may not be so to another. For a civilization accustomed to these effects, causality might be treated as conditional rather than absolute. This could influence everything from legal systems to storytelling, producing narratives where events are understood relationally rather than linearly. Religion and spirituality, if they arise, would likely be shaped by the ever-present horizon beyond which information cannot return. The event horizon could be interpreted as a boundary between worlds, between the knowable and the unknowable. Some belief systems might view it as sacred, others as forbidden, others as irrelevant. Pilgrimages might be made not to physical locations, but to observational thresholds, places where space-time curvature becomes especially pronounced and the universe reveals its deeper structure. Children growing up on this planet would never see a truly normal sky. Stars would shimmer and stretch near the black hole's silhouette. Constellations would not be fixed, but fluid, their shapes changing subtly over time. This could foster an early intuition that reality is not rigid, that appearances depend on perspective. Such an intuition, deeply ingrained, might make the society unusually tolerant of difference and contradiction. Despite all these differences, the emotional core of life would remain recognizable. Beings would form bonds, feel curiosity, experience loss, and seek understanding. They would look at the black hole not only with scientific interest, but with emotional resonance. It would be the first thing their ancestors saw when they looked up, and the same thing their descendants will see long after current civilizations have faded. In that continuity, they might find a sense of belonging that transcends individual existence. From the standpoint of the wider universe, such a planet would be difficult to detect. Its signals would be faint, slowed by gravitational redshift, and easily lost in the noise of galactic centers. Even if intelligent life broadcast messages, those messages might arrive distorted, delayed, or misinterpreted. Contact with other civilizations, if it ever occurs, would be strange and asymmetrical. Conversations could span generations on one side and moments on the other. This raises the haunting possibility that civilizations like this could exist unnoticed, living rich, complex histories in regions we have barely begun to explore. Our telescopes tend to avoid galactic centers, where dust, radiation, and gravitational complexity obscure observation. It is entirely possible that some of the universe's most ancient and stable biospheres lie hidden in these regions, quietly orbiting black holes while the rest of the cosmos rushes by. In the far future, when stars begin to fade and the universe cools, planets orbiting black holes might become some of the last habitable places. As stellar energy sources dwindle, black holes will remain, and with them the potential for extracting energy from gravity and rotation. Life that is already adapted to such environments could persist long after starbound civilizations go dark. In this sense, black holes could serve as refuges of life in an aging universe. This idea inverts our usual assumptions. Instead of seeing black holes as symbols of cosmic death, we begin to see them as anchors of long-term possibility. Not gentle, not welcoming, but enduring. Places where the universe's most extreme laws create niches that, while rare, are profoundly resilient. Ultimately, the question of life on a planet orbiting a black hole teaches us more about ourselves than about black holes. It reveals how narrow our definitions of habitability have been, how tightly we cling to familiar conditions. When we expand our perspective, guided by physics rather than fear, we find that life is not a fragile accident confined to quiet corners. It is a robust process that can take root wherever the universe provides structure, energy, and time. And in the deep shadow of a black hole, where space-time bends and time itself slows, those conditions may exist in forms more stable and enduring than anywhere else. As a narrative stretches farther into deep time, the idea of normalcy itself becomes relative. For beings born on this planet, the black hole is not an anomaly, but a constant companion, as ordinary as gravity underfoot. Their sciences would never ask whether life can exist near a black hole, because the answer would be written into every living cell around them. Instead, their questions would turn outward. They would wonder whether life elsewhere can survive without such an anchor, without such a powerful and stable source of order imposed by gravity. This reversal of perspective is important. What humans consider extreme might, in another context, be considered optimal. The immense mass of the black hole provides predictability on scales that ordinary stellar systems cannot match. Stellar systems are vulnerable to internal chaos, to resonances that destabilize orbits, to stellar evolution that dramatically changes energy output. A supermassive black hole evolves far more slowly. Its presence smooths large-scale motion, enforcing long-term regularity. For life that values continuity, this might be an advantage rather than a threat. The planet's orbit, though relativistic, could be astonishingly reliable. Year after year, cycle after cycle, it would trace the same curved path through spacetime. This reliability would allow biological clocks to synchronize not just with planetary rotation, but with orbital mechanics on scales far beyond a single lifetime. Migration patterns, reproductive cycles, and even neural rhythms might be influenced by gravitational regularities rather than solar seasons alone. Over time, the biosphere could become exquisitely tuned to minute variations in spacetime curvature. Some organisms might sense gravitational gradients the way others sense temperature or pressure. These senses could be used for navigation, communication, or even social signaling. To such life, gravity would not be an abstract force but a lived experience, something felt and interpreted directly. Intelligent beings with such senses would perceive reality in ways humans cannot easily imagine. They might experience space as textured rather than empty, time as elastic rather than uniform. Their art might attempt to represent these sensations, producing forms that seem incomprehensible to human eyes, but perfectly meaningful within their own perceptual framework. This highlights a deeper truth. Intelligence does not guarantee similarity. Shared physics does not imply shared experience. As their technology matures, they might develop ways to manipulate their environment with unprecedented precision. Structures could be engineered to exploit tidal forces for mechanical work. Transportation systems might rely on subtle gravitational gradients rather than brute force propulsion. Architecture could be designed to compensate for relativistic effects, ensuring that different parts of a city remain synchronized in time despite differences in gravitational potential. Such a civilization might also become acutely aware of fragility. Living near a black hole teaches respect for thresholds. Small changes in distance or energy can have disproportionate consequences. This awareness could foster a culture of caution, of careful measurement, of deep respect for limits. Recklessness would be punished not by social norms alone, but by the unforgiving nature of physics itself. Yet curiosity would persist. There would always be those drawn closer to the black hole, those willing to approach regions where time slows further and signals struggle to escape. These explorers would not expect dramatic destruction. Instead, they would encounter a gradual transformation of experience. Communication with home would lag. Processes would slow. Eventually, return might become impossible not because of force, but because of time itself. By the time they could come back, everything they knew would have moved on. This slow, silent separation could become one of the most poignant themes in their culture. Stories of explorers who did not die, but simply drifted out of shared time. Loved ones not lost to violence or disease, but to relativity. This is a form of loss uniquely tied to life near a black hole, and it would shape emotional expression in subtle but profound ways. From a biological standpoint, the slowing of time could even be used intentionally. Advanced medical techniques might involve placing patients in regions of slightly stronger gravity to slow biological processes during treatment. Preservation of knowledge, life, or even entire communities could exploit relativistic effects as a natural form of temporal shelter. This would blur the line between biology and spacetime engineering. As the universe outside continues its long evolution, the contrast becomes starker. Galaxies merge, stars exhaust their fuel, and cosmic expansion accelerates. From the planet's perspective, these events unfold with strange speed. Their astronomers would watch distant stars age rapidly, gaining an awareness of cosmic impermanence far beyond what most civilizations experience. This could instill both humility and urgency, a sense that while their local world is stable, the universe as a whole is fleeting. In the farthest reaches of time, when ordinary stars have faded into darkness, black holes remain. They become the dominant structures of the cosmos, slow-burning remnants of an earlier era. Planets orbiting them, if they still exist, might host the last pockets of complex life. These worlds would be cold, dark, and quiet by human standards, yet not devoid of activity. Energy extracted from black hole rotation or accretion could sustain ecosystems long after starlight disappears. In this ultimate future, life near black holes would not be an anomaly, but a norm. The universe would be shaped by its most massive and enduring objects, and life that learned early to coexist with them would have the greatest chance of persistence. What once seemed hostile would become home. This long view reframes the original question entirely. Life on a planet orbiting a black hole is not merely possible. Under certain conditions, it may be among the most enduring forms of life the universe can support. The black hole, far from being a symbol of inevitable destruction, becomes a cornerstone of survival in a cosmos defined by change. And so the idea settles into clarity. Life does not fear gravity. It learns from it. It adapts to it. It builds meaning within it. Even in the deepest wells of space-time, life can find room to grow, to think, and to wonder why it exists at all. In the end, the idea of life on a planet orbiting a black hole transforms from a shocking contradiction into a profound lesson about the universe itself. What initially appears to be the most hostile environment imaginable slowly reveals itself as a place governed by the same physical laws that allow stars to shine, planets to form, and life to emerge elsewhere. The black hole does not cancel these laws. It intensifies them, bends them, and exposes their deeper structure. In doing so, it forces us to confront the fact that habitability is not a narrow condition tied to familiarity, but a broad spectrum of possibilities shaped by energy, stability, and time. Life, as this exploration shows, is not fragile in the way we often imagine. It is not confined to gentle suns and quiet orbits. It does not require comfort or simplicity. It requires gradients to exploit, patterns to adapt to, and sufficient continuity to evolve complexity. A planet orbiting a black hole can provide all of these under the right conditions. Energy can come from stars, accretion disks, gravity itself, or chemistry hidden beneath the surface. Stability can arise from the immense mass of a supermassive black hole, whose slow evolution offers a steadiness unmatched by ordinary stars. Time, altered by gravity, becomes not an obstacle, but a defining feature, shaping biology, culture, memory, and meaning. Such a world would not resemble Earth, and that is precisely the point. Expecting life elsewhere to mirror our own experience is a limitation of imagination, not a rule of nature. On a planet circling a black hole, skies would be warped, light would curve, and time would flow differently depending on where one stands. Yet within this strange framework, living systems could still emerge, persist, and reflect on their own existence. They would love, struggle, learn, and wonder, just as life does everywhere it gains a foothold. The strangeness of their environment would not negate these experiences. It would give them new dimensions. The presence of the black hole would shape everything, from climate and evolution to philosophy and ethics. It would encourage patience over haste, continuity over expansion, and deep awareness of limits. Civilizations growing in such a setting might be less inclined toward rapid conquest and more inclined toward long-term stewardship. Their relationship with time would be intimate and unavoidable. They would know, not abstractly but viscerally, that past, present, and future are not absolute categories, but local experiences shaped by gravity and motion. This awareness could foster a form of wisdom rare in faster, more chaotic regions of the cosmos. From a cosmic perspective, these worlds challenge the assumption that extreme environments are barren. Instead, they suggest that extremes may harbor some of the most enduring forms of life. As the universe ages and stars fade, black holes will remain. Worlds that have learned to live with them may outlast civilizations that depend solely on starlight. In the far future, when darkness spreads and energy becomes scarce, life near black holes could represent not a remnant of a dying universe, but a continuation of it. Ultimately, the question of life on a planet orbiting a black hole reshapes our understanding of both life and black holes. Black holes are not merely cosmic destroyers. They are organizers of galaxies, anchors of structure, and engines of extreme but lawful physics. Life, in turn, is not a delicate anomaly clinging to narrow conditions. It is a robust process capable of inhabiting realities far stranger than our own, provided the universe allows room for adaptation. To imagine such a world is to accept that the universe is richer than our fears and more creative than our expectations. Somewhere, perhaps, a planet moves silently through curved spacetime, its oceans flowing, its skies glowing with distorted starlight, its inhabitants living full lives beneath the shadow of a black hole. They would not see their home as a paradox or miracle. They would see it simply as the place where they exist. And in that quiet acceptance lies the final truth. The universe does not care where life finds a way to begin. If the conditions allow it, even in the deepest gravity wells of space-time, life will rise, adapt, and endure.